So let's go ahead and start section 2.7, Applications to Computer Graphics. This section's a little bit artificial in that we're really working with geometry more than applying what we've learned to computer programming, but it still gives you a taste of what would be involved in working with graphical images that had to be programmed into some code. And so let's go ahead and start. We're going to start with a graphical image in R2. And I chose a trapezoid here, just a very simple shape to keep things from getting too complicated. And so the trapezoid passes through 0, 0, 4, 2, 3, 2, 1, 2. And we can represent that trapezoid with a matrix. And it's going to have columns that are the coordinates of the points on the trapezoid. So 0, 0, we have 1, 2, we have 3, 2, and 4, 0. And, I got a typo there. That's 4, 0 in that corner, not 4, 2. And we call this kind of a matrix is a data matrix. And it just contains our data. It just contains the coordinates of the 4 points of our trapezoid. If we had more points, we would have more columns to our matrix. I'm going to let A be the matrix 3, 0, 0, 1. And we want to describe the effect of A on the trapezoid. A is not a data matrix. A is a matrix of a linear transformation. So the roles of the two matrices are very different here. D just represents some information we have, some coordinates. A is a matrix that's actually going to do things, change things. In fact, let's calculate AD 3, 0, 0, 1 times 0, 0, 1, 2, 3, 2, 4, 0. And this you could do pretty quickly. We're going to get 0, 0, 3, 2, 9, 2, 12, 0. And let's now think about the columns as new points that we have. And let's think about plotting those. So we have 0, 0, 1, 2, 3, 4, 5, 6. And I guess I changed my scale a little bit here. We have 3, 2, 3, 2. We have 9, 2, so 4, 5, 6, 7, 8, 9. And we have 12, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so what's happened is our trapezoid, our original trapezoid, has had a horizontal expansion, or a horizontal stretch, you might say. There's no vertical change. I changed my scale here a bit. We're still sitting at points with coordinate 2 on the y-axis. So this matrix 3001 has had the effect of stretching the trapezoid out to the right. That 3 seems to be multiplying horizontally points or x-coordinates by a factor of 3, correct? In fact, if we compare D to our product matrix, the x-coordinates have been multiplied by 3, but the y-coordinates, the second entries, have stayed the same. Let's look at another matrix, B, 0, 1, 1, 0. And let's calculate BD. So again, this matrix B we're thinking of as a matrix of a linear transformation. And I went ahead and calculated this. It's easy calculation. I got 0, 0, 2, 1, 2, 3, 0, 4. And so what does my graph look like in this case? Still have 0, 0. In fact, notice how a linear transformation always leaves the origin alone. I have 2, 1, 2, 3, and 0, 4. So it looks like my trapezoid now is on its side. What's actually happened is, one way to think of it is, we have reflected through the line y equals x, or maybe an easier way to think of this is we've interchanged the roles of x and y. We've switched them around, interchanged the coordinates, the points. And you can see that comparing BD to our original data matrix D. And now I'd like to just think about what happens if we multiply B times A (3, 0, 0, 1) to get 0, 1, 3, 0 when you find the product of those two, and apply that BA product matrix to D. So we're going to take BA times D, which is 0, 3, 1, 0. 0, 0, 1, 2, 3, 2, 4, 0 was my original D. And I get 0, 0, 2, 3, 2, 9, 0, 12. And do a real quick sketch here. 0, 0, 2, 3, 2, 9, 0, 12. So what's happened is we've reflected through y equals x. And we've also incorporated that stretch. So I would say we have the combined effect of A and B transformations. So we see a composition of transformations to put the trapezoid in that position. Okay, so far nothing too complicated, but now here's the question we're going to try to address. What if we want translation? And by that I mean a shift, let's say horizontal, so not stretching, but shift to the right by, I'm going to pick a number here to work with, by 8 units. So no stretching. And that idea is we want our original trapezoid to shift down the line so that the 0, 0 point moves over to 8 and all the other points shift accordingly. 8 plus 4 would be 12 here, right? Well, we cannot do this with a linear transformation. And one way to see that we can't do that is the fact that linear transformation, whoops, I want to say in R2. And one reason for not being able to do that is because 0, 0 must stay put, must stay where it is. A linear transformation will never move the origin to a new location. But there is a way out of this, I'm going to call it a trick, of it's called homogeneous coordinates. And I'm not going to go into the meaning of or the use of the word homogeneous here because that would be too much of a side trip. I want to try to get us through this problem. So let's just go into what we're going to do. This is what we're going to do. We're going to think of R2 as the z equals 1 plane sitting in R3, three-dimensional space. So instead of an xy point or vector in R2, we're going to use x, y, 1. We're going to have a z-coordinate, but the z-coordinate is going to be 1. So instead of R2, the x and y axis, and say a point xy, which is just a flat plane here, xy sitting in the plane, we're going to work in space, go 1 unit up, and I'm going to try to use my artistic skills here to draw a horizontal plane, really just a copy of the z equals 1 plane, right? Or 1 unit up, the z-axis. And so that point xy in R2 will correspond to some point x, y, 1 in R3. There's my x-axis and y. Our 0, 0 point becomes the point 0, 0, 1. A linear transformation in R3 can move 0, 0, 1 because that's not the origin. The origin's down here at 0, 0, 0. So I just want to go back, do a bit of an aside here, and just go back to our A matrix, our first little linear transformation, 3, 0, 0, 1. And I'm not going to give an explanation of this. We're just going to make an observation, I think, here. We're going to set up a new larger matrix by putting A in the upper left corner. I'm going to put a 1 in the lower right, and let me just write zeros in each of these two positions. This symbolism actually represents a 3 by 3 matrix. I have the A entries in the upper left, 3, 0, 0, 1. This one means I'm putting a 1 in the lower right position, and these zeros actually stand for more zero entries. We just fill in the last row and last column with zeros. So this is actually a matrix that represents a transformation in R3. And if I multiply by xy1, so a vector in R3, but with z component, or third component 1, so it's sitting on that z equals 1 plane. If you go through this multiplication, we get 3x, y1. We get that horizontal stretch that we saw back in our beginning of this discussion. The y-coordinates don't change. The z's stay, at least for points on the z equals 1 plane, they stay the same. So by embedding that R2 transformation in R3, we're able to describe something going on in the z equals 1 plane. Now let's go back to our problem. So remember, we're 1 unit up. We're sitting on a copy of the z equals 1 plane, and we want to shift 8 units in the x direction. Translate 8 units. So I would like a point x, y, 1 to be transformed into x plus 8, add units to the x coordinate, nothing to the y, and the z is 1. Now we want to describe this change as a linear transformation in R3. So we need a 3 by 3 matrix. And without, again, getting into too much theory, I'm just going to try to describe how we can write that matrix down without too much trouble. I'm going to use the trick we used when we were describing general solutions to a system of equations. What we did was I'm going to write that x plus 8 as 1x plus 0y plus 8. In the second entry, y is 0x plus 1y plus 0. And the third entry, 1, I'll write as 0x plus 0y. So having coefficients of x and y in each case and a constant. And I hope this suggests the matrix with entries 1, 0, 8, 0, 1, 0, 0, 0, 1, okay, that we can multiply by x, y, 1. And it's kind of critical to have a 1 in this third entry, because it is sort of like we're taking 8 times 1, 0 times 1, 1 times 1 for those third terms in those entries. Because when you go ahead and check the multiplication here, we get 1 times x plus 8 times 1, so we get x plus 8 and we're going to get y for the second entry and 1 for the third entry. So here is a linear transformation of all of R3. 0, 0, 0 stays put. So in other words, I don't have to just operate on vectors of the form x, y, 1. I could use x, y, z, 0, 0, 0, anything at all. But these are the ones we're interested in this example, the x, y, 1 points. So just notice any point on the z equals 1 plane, which is a copy of R2 sitting in R3, is translated horizontally in the positive x direction by 8 units. So what we've found this 3 by 3 matrix to describe this transformation. It's a matrix of a linear transformation in R3 that's describing this horizontal translation of the copy of R2 sitting in R3. So I'm going to stop this part of the video. We're going to move on in our next segment of this lecture and talk about rotations.